In this tutorial, we're going to explore the process of building a mesh in TrueGrid for a tire by opening the tsave file, adding interrupts to the file, and then stepping through each command in the example mesh building process. We are going to illustrate the use of the history table to turn on and off commands. We will isolate commands that affect specific parts and isolate specific command types, such as a block boundary command, using the history table list feature. We are going to rotate a curve on a selected axis. We are going to examine the containing box by viewing the grid graphics. We will demonstrate the importance of the rest function to restore and recalculate the local coordinate system. Lastly, we will examine the transitions between parts with different element counts.
This is the file, and if you recall, I put an interrupt right here. We could look at each part separately. So indeed, the block boundary command is used. Here I put in some transitions, TRBB, and some more block boundary commands, and some more transitions, and some more block boundary commands. So what I'm going to do now, and oh, by the way, you'll see that it's been replicated 27 times. Each one of the parts has this replication command. From 0, reading the initial, all the way to the 26th. So I'm going to put an interrupt at the end of each one of these parts. They're all cylinder parts. This is naturally a cylindrical problem. So I'll put an interrupt right here. Sometimes it's better to have a command called end part. It really doesn't do anything other than it tells us this is the end of this part, but it helps you know where things end so you can put in an interrupt at the end of it. I'm going to put the end part commands in here right after the interrupt command. I think I've missed one. So here's our first part. Put a space in there. There's an interrupt there. An interrupt. There's an interrupt. Okay, so now I'm going to save this file and run it. Then I click on draw. Now here's the beauty of the history. We can look at all the commands to see how this was made. So I do history. Click on the history table. And you'll see that there are a lot of commands moving things around. And if I click here, I see, oh, there's an edge that I moved. And there's another edge that I moved. And then this edge and this edge. So these 4 outer edges were moved into position. And then I did a projection, SF. And I projected the entire interface to the torus. And then I projected the outer face to another surface. Let's look at that surface. It's probably a rotated 2D or 3D curve. It's surface number 62. So I will display surface definition number 62. And that's how it was formed, was by building a curve and then back to the input file. By the way, the history table does not have the geometry recorded in it. So you have to go back to the input file to see it. So here's 62, and it says that that is the union of 60 and 61. So we look at surface 60 and 61, and both of these are rotated 2D curves. That's what the CRZ is. Let's look that up. So we'll go to the surface menu, the SD command, and then we do a verbose. Remember that? Control V. Now looking for CRZ. There it is, CRZ. Means we've taken a 2D curve and rotated it around the Z-axis. So that gives us our first part. I'll remove all the surfaces. Did we use any block boundary interfaces? We have to look through it carefully, or we can. One of the things it can do is show us all of the block boundary commands in this part. And sure enough, there's a whole slew of block boundary commands in this part. Now, since it's the first part, it's most likely that all of these are master signs. Now, we could demonstrate some of these. For example, we could look at 100. I will do DBB for displaying a block boundary interface number 100. And it's right here. I could add 101. It's probably on the other side. There is 101. Well, sometimes what you have to do is label them, and then it becomes obvious. So we go to labels and label the BBs. We don't see it because we've highlighted this face with yellow. If I remove the highlighting, now we can see that block boundary. The block boundary interface isn't so tiny. It's just like this one we first looked at, but it's in the middle, so it's hard to see. The only time you can see it is in wireframe. With a hide, you only see the outer edge. Okay, now let's go to the second interrupt. So we click on resume. So this is a part made of two regions that are disconnected. Now we may want to see how this fits into the big picture. So what we can do is display all parts, that's DAP. We're looking at that first part after it was replicated. But if we go to fill graphics, it's not so difficult. Now we can see where these two regions of the mesh, this region here and this region here. Now after we finish this part, it'll be replicated, and so this will be filling in the space here and here, here and here, and so on, all the way around. So now let's resume to see the last part. There's our last part. Again, it's two separated blocks, small gap between them. And if we display all parts and do a fill, we can see how it fits in. And again, these will be replicated 26 times. When we had just that one part, we then had it scaled to fit in a box. And you can look at that box using the grid command. It's called the containing box. And all of the graphics parameters are relative to that box. And it's called grid right here. I'm going to turn the grid on so you can see the containing box. And everything is now relative to that. So when I display all parts, the aspect ratio is used and the cutting plane is used based upon the containing box of these two parts here. But our full model is much bigger than that. So when you try to display it, you get this great distortion as it whisks past behind your head and comes over your head and now back in front of you. It's an interesting effect, but it's not very useful. So what you do when you have this huge disparity between the containing box of the first picture used to show a much larger object, first thing to do is to click on rest. And rest will recalculate the containing box to include everything, and then the graphics behaves itself. So I'll show you that. I click on rest, and that not only recalculates the containing box, but also reorients everything so that the local coordinate system of the screen, X going to the right, Y going up, coincides with the coordinate system of our global part. And now when you rotate, you don't get that silly effect. And these two blocks are sitting right here. And they get replicated. And when they're finished replicating, we have this model. See the transitions right here? Because they were large here, there were 9 elements here, but they whittled down to 3 elements. In order to maintain a reasonable aspect ratio, we had to do a transition in between to compensate.